Critical numbers. That sounds important. They are. So we're going to look at a graph, and we're going to pick out three regions. A place where the derivative is greater than 0, less than 0, and equal to 0. So derivative greater than 0. So if you draw in the slope of the tangent, we want it to have a positive slope. So that would be this section over here. Anywhere else the slope of the tangent is positive? In here. So all these sections, we have the slope of the tangent being positive. We talk about positive slope, and it means that the graph is increasing. Slope of the tangent less than 0. So regions where the slope is negative. So that would be this section and this section. So when the slope of the tangent is negative, the graph is decreasing. What else is going on? Slope of the tangent equals 0. Well, if I'm not decreasing and I'm not increasing, then what am I doing? So the slope of the tangent right there is 0. And these have a lot of names. All right, so why is that? Let's talk about a stationary point first. The graph is decreasing, stops, then increases again. So that's why this point is known as a stationary point, because it's not moving anymore. It's not decreasing, it's not increasing, it's stationary. Same thing with this point. The graph was rising, then falling. This is where everything stops. Extreme point. Compared to the points around it, it's going to be the highest or the lowest in the region. Max-min point, a graph that looks like this has a maximum point right here. A graph that looks like this has a minimum point right there. It's the highest or lowest. A relative max-min means that in comparison to the points around you, you might be the highest point. Now, you're not the highest point on the graph because all these points are going much higher, but relative to points around you, you're a max or a min. Local max or min means the exact same thing. In this local area, this is the minimum value. In this local area, this is the minimum value. Are these important points? Oh, yes, that's why we call them critical points. So the definition of a critical point, it's a point where the slope of the tangent is equal to 0. Or the slope of the tangent does not exist. So how can the slope of the tangent not exist? I want you to look at this graph. If you're calculating the slope of the tangent line, when you're coming in on the left, you're saying, oh, that slope looks like it's -1. Coming in on the right, the slope looks like +1. At 0, the slope could be 0 or just about anything in between. So you can only have one slope. So this is a situation where the slope does not exist. So again, a critical point, it's a point in the domain of f of x, meaning a point on the graph, such that the slope of the tangent is equal to 0. Or rare situations, does not exist. There's also something known as a critical number. A number in the domain, such that the slope equals 0, or does not exist. That looks a lot like the earlier definition. So what is the difference between the two of them? A point is an xy value. A number is an x value. That is really the only difference. If I ask for a number, I just want x. If I ask for a point, I want xy. You find them both the same way. You take the slope of the tangent, make it equal 0. That'll tell us what the point is. And every once in a while, rare situations, we look for points where the slope does not exist. So how do we do these questions? I'll give you a function. I'll ask you to determine lots of things. A critical number, we set a point where the slope is equal to 0. All right, so let's calculate the slope. The slope is the derivative. So 3x squared minus 6x minus 9 plus 0. We want to make the slope equal 0, and then we'll solve that. These numbers are a little bit big. We could make them smaller by dividing by 3. Then we'll factor, and then we can solve. Answers, 3 and -1. So these are the critical numbers, numbers where the slope equals 0. Check. Intervals of increase and decrease. what you're going to do, you're going to put your critical numbers on a number line. And then we're going to look at the derivative. And you can look at the simplified version of the derivative as long as you have not changed any positive or negative signs. So dividing by 3 doesn't change positive or negative. And we're going to pick a number on the right of 3. So I'll pick 4. We're putting 4 in for all our x values. And all we want to know is when we plug in 4, does this derivative, because this is y prime is what this is equal to, this is y prime, is this y prime a positive or negative value? So we're putting it in 4 minus 3. 4 plus 1, positive times positive, positive. So don't actually care how big the numbers are, just whether they're positive or negative. Pick a number between -1 and 0. So when x is 0, we're putting 0 in the equation for the derivative. 0 minus 3, 0 plus 1, multiply a negative by a positive, you get a negative. Pick a number out here. And it doesn't matter what number you pick. No, as long as you are on the correct side, you can pick any number you want. I tend to pick easy ones. You are welcome to do the same thing. So we're putting -2 in. And where are we putting it? We're in for x in the simplified version of the derivative. So -2 minus 3 is negative. -2 plus 1 is negative. Negative times negative, positive. So this is what we know. We know that we have a positive slope on the left of -1, a negative slope between -1 and 3, and a positive slope on the right of 3. Now, for those who go, yeah, I don't really want to work with these points, this is annoying, there's another approach. For you graphical people, let's see how we're going to do this. Just have to find my mouse. Okay, for those who prefer to do graphs, you can decide that this derivative, simplified version, I'm just going to draw a quick sketch. X-intercept 3, -1. Parabola opens up. So again, what we're graphing is the derivative. We want to know where the derivative is positive. So that would be this section. So to the left of -1, on the right of 3. So positive. Where is it negative? That's anywhere it's below. So in between here and here, y prime, which is what the function is negative. So there's a negative. So for those who are good graphically, you can pick out the plus, minus, plus doing that. For those who don't want to do the graphs, you can do the number line. So where are we increasing? We're increasing anywhere the slope is positive. So from -infinity to -1 and 3 to infinity. Where are we decreasing? Anywhere the slope is negative. So between -1 and 3. Let's look at that one more time. Intervals of increasing when slope is positive. So that's where these come from. Decrease, anywhere slope is negative. So we're decreasing from -1 to 3. And again, these plus and minuses, we got them from y prime, so it tells us what the slope is doing. Positive slope, increasing. Negative slope, decreasing. Positive slope, increasing. Now let's talk about the critical points. So we want an x, y value. I'd also like you to tell me if this critical point is a max or a min. So if we're increasing on the left of -1, decreasing on the right, that looks like a maximum to me. And at 3, what's happening? Negative slope on the left, positive slope on the right, and that gives us a minimum. So when we calculate these points, we're going to find out that the point at -1 is a max and the point at 3 is a min. How do we calculate it? Well, when x equals -1, we're looking for a y value. The only equation with y is this one. It's a point on the graph. It's an xy value, so plug it in for y. So -1 cubed minus 3 times -1 squared minus 9 times negative 1 plus 27. I get 36 minus 2, 32. So I would say that the point negative 132 is a maximum. Let's do the same thing with negative 1. It's already done that. X equals 3 is the next one. X equals 3. Again, you want to know the y value, so you're putting 3 in for x. 3 cubed, 27. Minus 3 times 3 squared, minus 9 times 3, plus 27. Okay, I'm getting y equals 0. So we have a minimum at 3, 0. And if you think about it, what does a cubic graph look like? It's going to do something like this. So we have a maximum at this point, and the negative 1 would occur first, a minimum at this point, and that's where the 3 is. Okay, let's try that again. We'll do the same thing again. Critical number, slope equals 0. So we're going to calculate the slope of the tangent, and we have a quotient rule. Okay, so derivative of top times bottom minus top derivative bottom all over bottom squared. So 0 minus 1, so minus 1 over x plus 2 squared. We set that equal to 0 because this critical number is a point where the slope equals 0. We're going to solve this. Anytime we see a fraction, we'll multiply by that denominator. So we'll clean out the denominators, and then we can see what we're doing. When we do that, we're left with 0 on this side, negative 1 on the other. Now 0 and negative 1 don't equal each other. So we have a critical number when the slope equals 0, and it doesn't. So there are no critical numbers. Now, intervals of increase and decrease, we can draw a number line. But what goes on the number line if there's no critical numbers? Even if there's no number, you can still do this. And also with these kind of graphs, put in your vertical asymptote. Why do we do that? We're looking at how things are changing in terms of negatives and positives. And we know that when we cross asymptotes, that things change. So we want to know whether this is positive or negative when we look at the slope. All right, 2 ways of doing it. Pick a number on the right. I'll pick 0, it's a nice easy one. When I plug in 0, I get a negative on the top. 0 plus 2 squared is positive. So that's a negative answer. Pick a number on the left, I'm going to pick negative 4. Negative on the top. Negative 4 plus 2 squared, positive. So negative and negative. There's a slightly quicker way of doing that. So this is what we end up with, and let's look at the slightly quicker way of doing it. If you examine this, the top guaranteed to be negative. The bottom, because it's squared, guaranteed to be positive, which means the slope is always negative. For those graphical people, you'd like to know what it looks like. This has an asymptote at negative 2. The y horizontal asymptote is at 0. The y-intercept is negative 1/4. It would look like this. And then this asymptote, there's 2 of them, so we stay down here. And again, we are looking at this as y prime. So this is the graph of y prime. We want to know where y prime is greater than 0. It's not. Where is y prime less than 0? Everywhere, except for negative 2. Now be super careful when you describe the regions of increase and decrease. Increase, none, there's no plus signs. Decrease, minus infinity to minus 2, minus 2 to infinity. Some of you might be tempted to say everywhere. Why can't I just say minus infinity to infinity? And the reason you can't. Negative from here to here, negative from here to here, asymptote here. Let's actually look at what's going on with the original graph. Because when we talk about increasing and decreasing, we're talking about what's happening with the original graph. This one, y-intercept of 1/2. only one asymptote. So it looks like that. So when you look at the original graph, decreasing, check. Decreasing, check. But if you compare one point on the left to one point on the right, it's actually increasing. So that's why you have to say between negative infinity and negative 2. As long as you stay over here, the original graph is always decreasing. Or as long as you stay between negative 2 and infinity, the original graph is decreasing. So what I'm trying to say is that asymptote is crucially important, and you must separate these two regions. Critical points, take all your x values, none. So the critical points, there's also none. Oh, trig, your favorite and mine. We'll do the same thing. Y prime equals 0. Okay, derivative of 2 sine is 2 cos. Derivative of 2 cos is minus 2 sine. Let that equal 0. What happens if we bring the 2 sine x over, and then we could divide by 2 cos x. So why am I picking to divide by 2 cos x instead of 2 sine x? What's the difference? Let's find out. When we divide, we'll get sine over cos is tangent, and the other side is 1. So the reason I chose to divide by cosine is because we're better at tangent than we are at cotangent. It's the only reason. All right, where does tangent equal 1? For those tempted to draw the unit circle when you see the 1, be a little bit careful. I think tangent equal 1. It's when you have opposite and adjacent equal to 1. That angle is 45 degrees. Or if you're thinking in radians, we would call that angle pi over 4. So we know one answer is pi over 4. We always have to get all our answers. We're looking for all the answers between 0 and 2 pi. We know our first answer is pi over 4. The second answer, tangent, positive number. Where else is tangent positive? They're all tangent there. They're all positive there. Sine 10. Oh, it's down here. The tangent positive. It would have the same reference angle. So this angle is also pi over 4. And then when you measure your angles starting at 0 and rotating all the way around, how big is that? It would be pi plus pi over 4. So if you take pi plus pi over 4, get yourself a common denominator, we'd end up with 5 pi over 4. So our two answers, pi over 4 and 5 pi over 4. And those are places where tan will equal 1. Okay, so our critical numbers, pi over 4 and 5 pi over 4. Now we get to draw a number line. This time we're limiting it to only 0 and 2 pi. So don't go any further than that. We would like to know where the derivative is positive and negative. Now I think I warned you that if signs, as in plus or minus signs, are changing, you can't really use the simplified version. So because I've taken sine to the other side, I'm going to back up and look at this as my derivative. Okay, easy number on the left of this critical number is 0. I'm allowed to use it. It's the furthest left point on the interval, and it's not a critical number, so I can plug that in. So when we plug in 0, what do you end up with? Cosine 0, sine of 0. Let's do a quick reminder of how those work. At an angle of 0, I'm at 1, 0. That's my x value, that's my y value, that's my r value. Cosine is x over r. Sine is y over r. Okay, so the cosine of 0, x over r, gives me 1 over 1. I get 2 times cosine of 0, 1, minus 2 times sine of 0. Number is 2, positive. Okay, let's try 5 pi over 4. When you do 5 pi over 4, we're talking about an angle. Sorry, we don't want to use 5 pi over 4 because the answer is 0. We want a number in between. What's an angle, easy angle, between pi over 4 and 5 pi over 4? You could choose pi over 2. You could choose pi. I'm going to work with pi. No good reason. I just like that one. So we're going to put pi in this time for x. And when we put pi in, what do we get? This point is -1, 0. Cosine of pi, take x over r, so that's -1 this time. Sine y over r, that's 0. I said that was -1. So I'm getting negative for this region. Okay, next region. Nice easy number over here, 2 pi. That's a brilliant choice because that's the same answer as 0, which means it's positive. So what did we get out of there? We figured out where the slope is positive. So we're increasing from 0 to pi over 4 and 5 pi over 4 to 2 pi. And again, those intervals were given to us because otherwise we'd have to list a lot. And decreasing between pi over 4 and 5 pi over 4. So our critical points, I've given you the y values. Let's see if we can actually get those ourselves. So we want pi over 4 and we're plugging it into the original. Okay, so x equals pi over 4. What is our y? Y is equal to 2 sine x plus 2 cosine x. Calculate the sine of pi over 4. I think I'd use the special triangle that we had earlier. We knew the sides were 1, 1, and root 2. So sine of pi over 4, 1 over root 2. So 2 times 1 over root 2. Cosine of pi over 4, 2 times another 1 over root 2. So I'm getting 2 over root 2 plus another 2 over root 2, so 4 over root 2. Okay, when you put in 5 pi over 4, 5 pi over 4 and 5 pi over 4, all that happens are these become negative because we're in a quadrant where sine and cosine are negative. And that would give us the answer -4 pi over 2. So our two critical points, at pi over 4, we said it was 4 over root 2. 5 pi over 4, it's -4 over root 2. And how did we determine max and min again? The maximum and minimum, left-hand side increasing, right-hand side negative decreasing, therefore maximum. Left-hand side of pi over 4, negative slope, so that's decreasing. Right-hand side is positive, increasing, therefore minimum. Your job. Welcome to lesson 1. There's a lot of math here. If you're finding you're having trouble with trigonometry, come see me and we'll solve that problem. The calculus is actually not that bad. Again, all you're doing, slope of tangent equals 0. Then, where is the slope positive? Where is the slope negative? That's what gives you the increasing and decreasing. And then the x values you found for y prime equals 0, find your y as well. That's really all you're doing. It's not quite as scary as you might think. Off you go.